Okay, now part two. In part two, we are going to have a look how we can use GPU to do the computing. Uh, the the technology used by the GPU to do computing is called a single instruction multiple threads, SIMT, single instruction multiple threads. This is Nvidia's data parallelism. It's also AMD's data parallelism. It's exactly the same thing. So how does it work? Is not so difficult to understand. Let's start uh, by reading this picture. So you have a C program, you have a sequential execution program. Okay, you start execution of your code. At the beginning, it starts with sequential execution. You have a serial code, and this code is going to be executed by the host, means by the CPU. And here you have only one thread. And at the moment, you feel you need to use the GPU to do the computing. What you are going to do? Okay, what you need to do is a parallel kernel functional call. So device means GPU. So what do you need to do? You want to use this GPU to help you to do the computing. What you need to do is to do a parallel kernel call. Parallel kernel call. So this is calling the kernel 10, and now kernel 0, and with parameters, you call this kernel. And then what you are going to have is that you are going to have lots of threads. Here you have the threads, 1, 2, 3. You have lots of threads, because I have said that GPU computing is to use the threads to explore the data parallelism. So for GPU, you are going to have lots of threads, much more than the hardware units you have. And then you are going to use all these threads to help you to do the computing. Okay, and then after the job has been done, you don't need to use the threads anymore. And here you are going to come back to the zero part of the code, the code. And you are going to back to use the CPU. After the GPU has done the job, the CPU will continue. The CPU will continue to execute your C code, and is going to come back to the host. You still have only one thread, because you started with only one thread. At the moment, you need a lot of threads, and you ask GPU to help you. You ask GPU to give you threads. Now, again, it's the same situation. You need to call kernel 1, and you need to have lots of threads, and the GPU will come in. This is GPU. Sorry, I'm not used with this writing here. So this is GPU. And you are going to have lots of threads to help you. After you have done your job, the threads will be terminated again. And this is the way for you to use the GPU. Basically, it's called offloading. You have your program running on the CPU on the host. From time to time, you need to use GPU. What you are going to do? You are going to do an offloading. Means you are going to give some workload to the GPUs. And the way for you to offload the workload to GPUs is the kernel functional call. Okay, now before we move forward, we need to compare this one with the one we have discussed in the CPU part. Okay. So I've said that to justify the use of GPUs, it's better you have a workload that needs at least 1 million threads to work on. You need to have a big workload to offload to the GPU and for the threads to work on that. And this workload has to be enough for 1 million threads, minimum 1 million threads. It's worth doing if this is the case, because the fact is that when you do the offload from the CPU to the GPU, is kind of offloading. Workload offloading usually means you need to transfer the data from the CPU memory to the GPU memory. So this is the offload, and that takes time. To make it worth doing, I mean, to make the GPU computing worth doing, you have to offload enough workloads for at least 1 million threads to work on for a considerable amount of time to worth it. Okay, because if you offload a lot of workload, you are going to need a lot of memory bandwidth, and because you have 1 million threads to work on the workload. Usually the workload means data. If you have 1 million threads to work on some workload, they are going to attack the memory system, and the memory system has to have a quite high bandwidth to withstand this kind of attack. And here is the reason HBM comes in. Okay. Anyway, this is the fact. But we discussed this one is that this is the data parallel region, and we fork a lot of threads. And when we have done the job, what we are going to do is the threads are going to join the master threads. I mean, the threads that has been forked will be killed. This is something we have discussed in the section 1, part 2. Okay. Now, if you compare this one with the GPU, do you see any similarity? Yes, it's nearly the same thing. It's the same thing. So for CPU computing, when we have only at the beginning we have only one thread, it means here it's the same thing. At the beginning you have only one thread, thread 1. You have, sorry, thread 0. You have only one thread. Here you have thread 0. And then you need to help. You need to work on a big workload. What you need to do is that you ask the system, or the system is going to create a lot of threads to help you. So start from ID 1 to ID n-1. That's the threads created by the system to help you. The functional call used is fork, and then after the workload has been done, all the created threads will join the thread 0 to come back to the fact you are going to have only one thread. So here you have a thread. Sorry, I'm missing away thread 0 back again. If you just look at this part and this part, you compare this part and this part. What's the difference? What's the similarity? The similarity is that for CPU computing, for OpenMP, when you need to have a lot of threads, the system is going to create a lot of threads. Each thread is going to be executed on a call to work on a piece of workload. For GPU, the fact is that when you need to have lots of threads to help you to work on the workload, you are going to ask GPU to create lots of threads, and all these threads are going to work on the workload you want them to work on. Okay, so the reason we have lots more threads is that you need to have all these threads to work on some kind of workload. And here is the same thing. They need to work on some workload and share the workload between all these threads. And that's the same thing here for GPU. The workload will be shared by all these threads. So conceptually, if you look at this GPU computing, if you look at this single instruction, multiple threads, conceptually, it's so easy to understand. The fact is that it's so much similar to the OpenMP computing, the thread computing, the shared memory computing, is that when you need to when you have a workload that need to be worked on by lots of threads, you just create threads for CPU computing, or you just call the GPU to help you, because the GPU they can have lots of threads. So conceptually, it's easy to understand. How this could be done? Let's move on. Okay, here is a piece of sample code. This code is going to explain to you how this will be done. Okay, you have a C programmer. This is the starting point of C programmer. You start the executing of the C program, and your program will be executed here with only one thread. Now, where is only one thread 0? Okay, and then you need the help of the GPU. You have a big workload. You need to help. You need to use GPU to work on this workload. What are you going to do? You need to do a functional call. Okay, this is the functional call. How does it work? Here, basically, you need to define the kernel functional. This is the kernel functional definition. Basically, is kernel definition. So you need to define this kernel function. It's called matrix addition. What it's going to do is that you have two vectors. No, you have two matrices. You have two matrices. The matrix A, let's say, is like this one. You have an element A 00, A01, A02, A, the last one, let's see, N minus 1, and you have A10, and A11, A12, etc. This is A0, sorry, A0 n minus 1, and this is A1 n minus 1, etc., etc. And you are going to have AM0, AM1, AM2, etc., etc. And the last one will be AM minus 1, n minus 1. This is the matrix. And you are going to have another matrix. The B is the same thing as the A. This is B matrix, B matrix, B matrix, B matrix. Okay. And then you are going to sum the two matrices and put the result in C. This is what the kernel function is going to do. And as a programmer, the programmer has to write this function in their code. They define this function, and then when you have this workload to work on, basically you are going to call this kernel function. So you call this matrix add kernel function. This kernel function call is a little bit different than the traditional C functional call, because these are the parameters for the functional call. And here we have some strange parameters here between the triple chevrons. Okay, you have number of blocks, threads per block, etc., etc., etc. These are the parameters for the kernel functional call. The reason for us to have these parameters is that because you have lots of threads, you have to have a way to organize all these threads. The easiest way to organize these threads is by put these threads into groups, into blocks. So the, the here you have a grid of threads. You have a two-dimensional grid that match the fact that you have a two-dimensional array to be added. So you are going to organize all these threads into two-dimensional arrays, two-dimensional grid. So you have the grid 0, and then you have this block. You are going to organize your threads into blocks and blocks into grids. And if we look at this one, the x direction, you have how many blocks, and the y direction, you are going to have 2 blocks. And here is passing the thread organization into this functional call. Okay. That has been done. Now, up to this point, the workload will be offloaded to the kernel. The kernel need to work on that. How it's going to be done? Let's have a look. Continue. These are the numbers that you need to pass to the functional call, the kernel functional call, that tells the kernel function how the threads will be organized. Okay, and then now we move to the kernel function. Basically, the kernel function is going to have the parameters as A and B and C. That are 3 matrices. Okay. Now the fact is that you have lots of threads. Suppose this matrix is 1024 by 1024. Means n here is 1024, and that means you have 1 million. You have 1 million elements. You have 1 million elements for each matrix. Okay, suppose you ask the GPU to give you 1 million threads. That's fine. And that means we have 1 million threads, we have 1 million elements. I can ask each thread to work on 1 element. So I'm going to ask each thread to work on A, I, G plus B, I, G. Sorry, this is I, and put that result in C, I, G. So that's possible. We have each thread to work on only one element. So that's fine. So, but the fact is that you have 1 million threads, you have 1 million elements. How you are going to ask each thread to work on which element? How they are going to know that? How that's going to be organized? So that's not difficult, because when you are telling the kernel functional call you have 1 million threads, the threads will be organized into blocks, and within each block, the thread is going to has its own ID. So you have a quantity of blocks, each dimension. You have the block ID for X and block ID for Y. Okay, and then you have the thread ID for X and Y. So the facts, this is very similar to the Cartesian system, is that you have organized the threads into this two-dimensional grid, and each thread should be able to be identified by using their let's see their um, Cartesian system by a Cartesian system. So each thread should have its x and y position. We can understand that they have their x and y position, and we so we are going to use this x and y position to ask each thread to work on a um, particular element. Okay, so we use the threads um, position, and we do this calculation. Just remember that when you are calling the kernel function, after you have passed these parameters to this kernel functional call, and each thread is going to have their block position, which block they belong to, and what's the thread position within within a particular block. Now, so for example, we take an example here. This thread here, which is in the second block in the x direction, and the second block in the y direction. And the thread within this block, it has its own position. So by using this block position, we can work out if you look at these threads like within this two-dimensional array, you can find out the position of each thread. You are going to work out their I and J. Basically, you think that you have this, even though the threads has been organized into blocks, and the blocks has been put in this grid, two-dimensional grid, you can think each thread is within a Cartesian system. Each thread has its own position, x position and y position. X position is I, y position is j. You use this formula to calculate their x position and y position. So, for example, if you have, after you have done that, each thread is going to have a unique I position and j position, x position, and y position. Okay, but that's good enough because right now you have 1024 for x position, and for y direction you have another 1024. So you have 1 million. I mean binary million. You have 1 million threads, and you have 1 million elements. The fact is that each thread is going to use their x, y position to find out the element they need to work on. And then, so each thread is going to execute this piece of code. So each thread is going to work out its own I and its own j, and then each thread is going to find out the element with the I and j as the index, and the B element with the I and j as the element, and it's going to do the sum of these two elements, and then this thread is going to put the final result in the matrix C in the corresponding position. Each thread is going to work on only one summation of two elements. So that's the job for each element. And then the job will be done. Each thread is going to run these lines of code, and each thread finally is going to work on only one element. And because if you have 1 million elements, and if the operation takes only 1 unit time, and then the 1 million elements, the summary of the two matrix will be finished, will be done in just 1 unit time. So that's going to be very fast, because you have 1 million times faster than you have to go through to loop through each element and do the summary, do the sum. Here, there is another line code we need to just try to understand. Here is that we have this I, we need to guarantee the I is less than n and j is less than n. The fact is that, we know that for the GPUs, the threads are scheduled in the group of 2. So if you ask we take this as an example. It's better I change the color. Suppose right now that you have 1,000 elements. N is 1,000. So then you have 1 million. You have 1 binary million elements for the matrix. For each matrix, you have 1 million binary million elements. But the fact is that if you do the kernel functional call, you ask for, pretty much you ask for 1 million, 1 binary million. Sorry, I'm really sorry. I made a mistake. So here is that this is decimal million. I'm confused. So what I'm going to say, what I'm trying to say, that you have n is 1,000, and you are going to have 1 decimal million elements. Okay, and later on you are going to ask the GPU to give you 1 decimal million threads, because you have only 1 decimal million elements. You don't need to ask more than 1 decimal million. But the fact is that because the threads are scheduled in a group of 32 threads, that's a warp for Nvidia GPU. So if you ask for 1,000, the system is going to give you 1 binary. Is going to give you 1 binary million threads. That means you are going to have 1,024 times 1,024 threads. And the threads is going to be organized into grids. And then later on, you are going to use these 2 line codes to calculate the I and j. And then the fact is that because here, this is the matrix. This is here, the last element will be, if we look at the matrix, because here is 1,000. Let me just do it better, nicely. I just need to gom it. Your matrix is going to be, sorry, I need to do, your matrix is going to be 1,000 by 1,000, and the last one will be 999,999. That's the last matrix element, if that's 1,000 by 1,000. Okay, but the fact when you are going to ask a system to give you the threads, your threads will be organized into the grids, and you are going to use these 2 lines of code to calculate which element your thread will be working on. But we are going to have the situation that the threads will be, oh, now you can think that the threads, finally, the thread, there is one thread is going to be working on the the element 0, 0, okay, 1, 1, 1, 0, 0, 1, okay. The threads will be like this. And then the last one, the thread should be supposed to working on the um, the last elements. Okay, and this one will be on this one. So and then the last one will be this one. So the fact is that you have more threads to work on the matrix, but because the matrix you have 1 decimal million elements, and actually what you have as threads, you have 1 binary million threads. Okay, so the fact that you ask each thread to work on the elements, you have more threads than the elements, so you have to check whether the thread has been supposed to work on, whether their position is within the matrix limit. So if this, for example, we take the last one, we have a thread which is with I is 1023 and j is 1023, and we are going to find out that this 1023 is bigger. It's bigger than what? It's bigger than 999. Okay? Then that means for no threads with their I with J ID is bigger than 999. They are going to have nothing to work on. They are going to do nothing. They are going to find out, okay, I have nothing to do. I'm going to just do nothing. This is going to be what's going to happen. Okay, so we have gone through this piece of very short code. We spent quite some time to understand this one. Basically, it's not so difficult to understand. Okay, so we move on. We have another example, which example from AMD. We just go through this example. It's roughly the same idea of the previous one, but we just have a look at this one, and it's going to help you to understand. Here, the fact is that what we are going to do is that we are going to do the summary of 2 vectors. And this vector, I have turned this picture 90 degrees. I have made to make it a vector. So what the system is going, what the mathematics is that you are going to do b vector b plus c and put the value in a. So the b is 5, the c is 3, and the result is going to be 8. Is going to be put in a. This is the mathematics that this piece of code is going to do. For AMD SIMT single instruction multi-thread, so calling the GPU, you have to use this software solution from AMD, which is ROCm. Is called HIP. You are going to use HIP API, heterogeneous computing interface for portability. This is the HIP, heterogeneous computing interface for portability. This is something the same as CUDA. CUDA is for Nvidia, but for AMD, this is a HIP. And this is in this RockM solution package. So we are going to have a look at this one. That's the same thing. We have host and the device part of code. The code could be the code, you have part of the code will be executed on the host, another part of the code will be executed on the device. Device means GPU. So it's the same thing as Nvidia. So we are going to understand the kernel offloading of AMD. Basically, it's the same thing. So you start run this program, and you are going to have only one thread running this program. You start with thread 0, and then later on, at a point, you have quite a lot of workload. You need to have lots of threads to help you. So what you are going to do, you are going to do s a plus 1 a multiply x multiplied by a plus y, which is the sum. So you are going to do this kernel functional call. And what you are going to pass to this kernel functional call is the a, the x vector, the y vector, and you need to tell the kernel functional call what's the size of the vector. And then the same as CUDA, between these triple chevrons, you are going to have some kind of strange parameters. Actually, these are the parameters to tell the kernel functional call how the threads created by the GPU will be organized. And this one, basically, what you are going to do is that you are going to do a plus x. You are going to have a vector is x. You are going to use a to scale the x, and you are going to multiply the x by y. You are going to put the result. This is the final result is going to be somewhere. So you are going to put that in y. Here, the fact is that this is vector y, and this is vector x. You scale the vector x by a, and plus the vector y, you put the final result in vector y in this position. So this, no, you start executing, you start to execute this piece of code. At some point, you are going to do this kernel functional call. And with these strange parameters, the system is going to be able to create the threads and organize the threads. The same idea as we have discussed for CUDA is that here, right now, you are going to create quite a lot of threads. Each thread is going to execute this kernel. Okay, so you have a is floating point number. You have this vector which is x. You have this vector which is y, and this is the size of the vector. Okay, and then each thread is going to calculate its global ID. This one is a little bit different than the previous one. In the previous one, what we saw is that the threads are organized in a two-dimensional grid. Okay, two-dimensional grid. Because right now here you are working on vector, so the threads, they don't need to be organized in a two-dimensional grid. They could be organized in a one-dimensional, just one-dimensional. I mean, in dimensional y. So you are going to have a house x0, x0, x1, x2, etc., etc. X, let's see, is 999. You have Y0, Y1, etc., Y 999. And the last result will be put in Y9, 99 and 99. Okay, so the same idea as for the previous example, what we are going to do is that we are going to take the organization parameters of the threads, because the threads will be again organized into blocks. But this time, because you have only you have vector, so you can arrange your blocks in a vertical line. So you don't have the blocks in the y dimension. In the y dimension, you have only one. You don't have the y dimension is always 0, so you don't need to take this y dimension into your calculation. And then by using this block, the organization information, each thread is going to calculate their global ID. So if you have 1,000 elements for your vector, if you ask the system to give you 1,000 threads, the system is going to, at the end, will give you 124 threads. And the threads will be organized. Let me change the color. So you are going to have the threads. The threads will be organized like this. The threads will be organized thread 0, thread 1, etc., etc., thread 1023, because you have got 124 threads. So your threads will be, they are going to be organized into blocks. And then that information will be passed to the GPU with this block information. The arrangement of the threads will be organized into blocks. And within each blocks, you have multiple threads. And with this kind of arrangement, with this kind of information, each thread is going to calculate a global ID. Basically, each thread is going to do the calculation. They are going to have a value as 0, a value as 1. And because you have 124 threads, the last thread is going to have the value as 1023. So each thread is going to have a global ID. You can just think that the thread has been arranged in linearly, vertically, with different thread number and thread global ID. And the last thread is going to be 1023. The last thread will be this one. Okay, and then now you are going to pass this, the threads, they have worked out their global ID, and they are going to use this global ID to find out which vector elements they need to work on. Thread 0, they are going to use 0 as the index to find out the first element of each vector. So thread 0 is going to find out, I'm going to work with x0 plus a, x0 multiplied by a plus y0, and I'm going to, thread 0 is going to put the final result in y0, this position. And thread 1 is going to work on y1 plus x1 multiplied by a, and put that in the y1, etc., etc. And thread 999 is going to work on a multiply x 999 plus y 999 and put the final result in y 999. And then this is the condition for this for threads to decide which one for them to work on. If the thread they are going to, there are some threads they are going to find out that their thread their global ID starts from 1000 up to 1023. All these threads, all these 24 threads, they are going to find out they are out of the range of the vectors. So that means they are going to do nothing because they have nothing to do because you have more threads in the workload. And then these threads will stay we'll just be there and check they are out of range of the vector and they are going to do nothing. Okay, so for that to be easy to understand, I turned this this vector, because this is the vector has been shown horizontally, and I have turned that 90 degrees just to show you this is the how it works. So this y is going to be this y is going to be a multiply x 0 plus y 0 and put that in 1 y 0, and this one is going to be like this. The last one is going to be let's see, this is the last one is going to be 3 9 and 9 is going to work on x 909 plus y 999 a scaled by a and put that in 999. Okay, so now back to the offloading for the SIMT offloading. It's easy to understand. So you can just think that you are running a sequential program, and at a point you have to offload your workload to the GPUs, and the GPUs is going to create lots of threads to help you, and you have to some kind deal with the arrangement of the threads, because you do have lots of threads. You need to have a way to arrange these threads and ask each thread to work on a different workload. For our examples is that you have to ask each thread to work on a different vector element or matrix element to share the workload and then to give you the final result. After this kernel functional call has been done, then you don't need to have these threads. The threads will be killed, and then you continue your computing as a sequential program. So this is the way for the CPU for Nvidia and for AMD to offload their workload from CPU to the GPU. This is called kernel offloading. So for the programmers, they have to deal with this kernel offloading, and they have to write these kind of kernel functions. They have to call these kernel functions from their code, and they have to write these kernel functions to arrange, to organize all these threads to share the workload. So there is something, this is a little bit strange at the beginning, is this kernel functional call is going to be called with these strange parameters at the first look, because this is the arrangement of the threads. And then afterwards, after you have worked out this kind of concept, it's not so much difficult for us to understand. Okay, we move on. Here just try to explain that on the marketplace to do this kind of SAMT calculation, functional call, kernel offloading, kernel offloading, I think this is of kernel offloading. Basically, there are mainly two software development keys to help you. One is CUDA from Nvidia. The other one is HIP from AMD. They are very, very much similar up to the point that for a particular program, AMD listed the similar, no, okay, they are too much similar. If you go to the website of AMD, AMD listed the similarity of NVIDIA CUDA and AMD HIP. Basically, what AMD has done is that they have listed this this CUDA stuff. Okay, this is the functional core. So CUDA free is functional core. This is the data type. CUDA arrow, this is the data type. And we have, I recognize this is a functional core. And this is a functional core. Every functional core is started with the CUDA. So CUDA kernel functional core. This CUDA functional core. And this is the data type. And at the same time, at the other end, the AMD listed that the corresponding HIP data type and the HIP functional core. So the CUDA malloc functional core, the corresponding HIP functional core is HIP malloc. Okay. The CUDA event record functional core, the corresponding functional core from HIP is HIP event record. So they are not just similar, they are the same thing. If you have a CUDA program that has been written by using the CUDA SDK, and you want to move to the AMD platform, basically, if you are not using some very specific CUDA functional calls, some specific features from CUDA, basically what you can do is you just replace the keyword CUDA by HIP, and you recompile your code. Your code should be able to execute on the AMD GPU. Okay? So this is the similarity. It's not just similarity, because AMD is following CUDA and they want to make things simpler for the programmers. Basically, they want to the users of CUDA, the users of the NVIDIA GPU to move to later GPU platform. So they have developed their system exactly as CUDA, except they have less features and less functional calls. And even I think for the library is the same story. Most CUDA libraries have a corresponding HIP library. So CUDA plus library, you have a HIP plus library. The ROC plus library, the CUDA FFT library, you have a HIP, you have a ROC FFT library. In the case where a library provides ROC and a HIP version, you have for AMD, the plus library, you have a ROC version and a HIP version. The HIP version is a marshalling library, which is just a thin layer that's redirecting the functional calls to either the ROC library or the corresponding CUDA library, depending on the platform, to provide compatibility. Okay, that's easy to understand. So, but basically, here, what I want to show you there is that the two systems are nearly the same, and AMD is always following Nvidia regarding this library. So the fact is that if you are not using some very specific features coming from Nvidia, coming from CUDA, you can migrate your code very easily from I shouldn't say very easily. You can migrate your code from Nvidia platform to the AMD platform, and even AMD has developed a tool to help you to do that. And the tool, if I didn't make any mistake, the tool is called HipFi. HipFi is the tool to help you to move from CUDA to HIP. The tool is called HipFi. So I just want to mention here is that we have the Nico library and we also have this Rico library. They are exactly the same thing. We are going to discuss this later on, so I just want to point out here. Okay, kernel offloading, which has been used by Nvidia and AMD, but there is another offloading which is OpenMP offloading. Kernel offloading is for CUDA, is for HIP, but there is another way to offload the workload from the host to the device. That means from the CPU to the GPU, which is the OpenMP offloading. So means that that's the same idea. If you remember that we have discussed the OpenMP programming, basically, if you have an OpenMP program, you start running this OpenMP program, and you are at the beginning you are going to have only one thread 0, and at a point you have a big workload. You need the help from other threads, and the system is going to create a lot of threads. You still have the thread 0, and the system is going to create threads as you wished. You tell the system how many threads you are going to need. You are going to have another thread, T2, you are going to have lots of threads, Tn. Okay, and this thread is going to work on the same workload. I need to change color back to the red. And these threads will be working on the workload. Sorry, I need to correct myself. Sorry, I'm not so much used with the tool here. I'm sorry for that. So here I need to change color back. Yeah, it has been done. Sorry, I didn't. I'm sorry. I'm not used with this tool. GOM. So workload. All these threads will be working on the workload, including thread 0. After the workload has been done, and then again, we continue, we are going to have thread 0 and all the others will be killed. And we have discussed this one in the section 1, part 2, and this is exactly the same as GPU offloading conceptually. So for OpenMP, if you can do that, because all these threads will be created by the system, and all these threads in the color blue will be executed on the CPU cores. And this is for OpenMP. Okay, this is for OpenMP. Now, if we follow this concept, my point is that if the OpenMP can have some way to create threads, I mean, to basically the concept is the same thing. You have a thread and you need to have lots of threads to help the thread zero. That's basically is exactly the GPU is doing. So for OpenMP, the OpenMP is a standard and is an organization. For them, they should be able to do some development to have this OpenMP to off their workload, not only to the CPU, but also to the GPU. Because the offloading is the concept to have more threads to work on the workload. For OpenMP with threads running on the cores, conceptually is the same thing for OpenMP to have threads comes from the GPU and working on the workload. So that is naturally easier, conceptually is naturally easy for them to deploy this one, to evolve their standard. And that has been done. So let's just read this piece of code, how this will be done. Okay, so this is a piece of code, C code, and then we have this NX, which is 1000 and 2400. Okay, we start with the main point. We start to run this piece of code. This is the starting point. We declare the vectors. We have vector A, B, and C. What we are going to do is that each element of vector A is going to be multiplied by vector B, and then the result will be put in C. I think it's not so much better than, because here we need to have A0 and B0 and C0, because this is the C code. And this, the last one should be -1, -1, and -1. This is going to be easier to understand, to match the code. So this is the mathematics. What we are going to do is A multiplied by B and put that in C. And it has been shown here. Okay, you start running the code. So initialization of the vectors, you prepare the data. And then the two vectors need to be dot product. You need to calculate the dot product of the two vectors. Okay, so if you basically if you have just a sequential program, what you need to do is you need to loop over all the vector elements from 0 to the last one, which the last one will be nx minus 1 from 0 to the last one. You loop over all the elements. You are going to do the dot product of each element, and you put the result in the vector C. That's for sequential program. For OpenMP, because we put this programmer OpenMP here, if we are running this piece of code on a server with multiple cores, suppose you have 128 cores. You can ask the system, you have already thread 0 here. You can ask the system to create another 127 threads to help you. And that totally you are going to have 128 threads. The 128 threads is going to work on the 1,400 elements of the vector. And basically, if you are not doing that on the GPU, and the system is going to give each thread a piece of the workload to do. So let me just do the calculation. This is total elements divided by 128 threads. If you have 128 threads, 12400 divided by 128 threads and 800. The result is 800. So starting from 0 up to 799, one thread will be working on 800 elements. That, for example, thread 0, and thread 1 will be working on another 800 elements, and thread 2 another 800 elements, and up to the end, the last thread will be working on another 800 elements, and the job will be shared by 128 threads running on 128 cores if you have your system with 128 cores. So this is the traditional OpenMP code, traditional OpenMP programming using only CPUs. Okay, and afterwards, what I are going to do is that you need to loop over all the elements of C and you do the sum. So here you calculate the sum. You loop over each element of the C, you are going to get your sum. You output this sum, and this code will be terminated at the end. So this is how you are going to work with traditional system with 128 cores. Now, suppose we have a GPU with the system. Instead of offloading all the workload to the 128 cores, what I'm going to do is that I'm going to workload the workload to GPUs. So what? Sorry. Okay. Maybe it's better to keep this one. Anyway, it has been done. Okay. So now what I'm going to do is that I'm going to offload all this workload to the GPUs. What I'm going to do, what I need to do is that I'm going to put a keyword target. That means right now the OpenMP is not going to ask other threads. The system won't create another 127 threads to join the first thread. You have a total 128 threads running on 128 cores to share the workload. I'm going to ask the GPU to do the computing. So here you have this keyword is for GPU, means here this for loop should be offloaded to the GPU. Target pretty much means GPU. All this vector operation will be done, should be done by a GPU. You need to offload this to the GPU. Okay, that's fine. And then, okay, if you offload to the GPU, things will be different because here you have 1,000. Okay, maybe make things easier. We have another 0. We put another 0 here. Suppose we have elements. We have elements. The vector we have 1,024,000 elements to be done. What the system is going to ask the GPU to do is that, okay, GPU right now is up to you to do this calculation. Then the workload will be offloaded to the GPU, and then basically this is called directive offloading. For um, for 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 CUDA and HIP, up to now we have been talking about this kernel offloading. For kernel offloading, you have to write the kernel function, and you have to call this kernel function from your code. But for directive offloading, what you need to do is that you need to put in the directive the keyword and some parameters to tell the runtime system to offload the for loop to the GPU. Okay, and then basically the GPU the GPU you need to ask the GPU will create one binary meaning 0, 1, 2, 3, etc., one binary meaning threads. That's going to be threads. The last thread will be 1 minus 1. So the last thread will be with this number. So the last thread, you are going to have this quantity of threads to work on your 1,024,000, okay, sorry, 1,024,000 elements. So basically, we are going to repeat the story that has happened with kernel offloading, and your vector is going to be with element 1, 2, 3, etc., etc. And the last element, the ask vector, vector 0, vector 1, vector 2, is the element of the vector. And the last element will be 1. Okay, this is the last element of the vector, and the GPU is going to create threads with one binary meaning threads. One binary meaning threads because you have more threads than the vector elements, and you are going to have all these threads here. They are going to be free. They are going to have no workload to work on, so they are going to do nothing, and you are going to have all the other threads. They are going to work on the corresponding element of the vector and put the result back into C. So you are going to do A multiplied by B and put that in C. And as a programmer, they don't need to write the kernel function. They don't need to call the kernel function from their code. What they need to do is that they put this target, tell the runtime system that this offload will be to the GPU, and pretty much except this target parameter, the programmer need to put here some more parameters to tell the runtime system how you are going to offload the workload to the GPUs. Okay, so this is called directive offloading. This is called directive offloading, means that the programmer is going to use the directive to tell the runtime system to do the offloading. And this has been put into this OpenMP standard. Right now, the OpenMP runtime system, some vendors, their runtime system can do this kind of directive offloading. Okay, so we move on. There is a picture to show this directive offloading. This is directive offloading. I've said that it seems to be simpler because here the programmer, they don't need to write the kernel function. They don't need to call this kernel function and pass to the kernel function the strange parameters between the triple chevrons. I mean the parameters to tell GPU how to organize the threads into blocks, etc., and later on into grids, etc. You don't you don't need to deal with all these complexities, these kernel functional call complexities, but you just need to use the directive to tell the runtime system to do the offloading, and the runtime system is going to do the offloading automatically for the programmer. But it's not simple. Right now, this time with directive offloading, the complexity is with the OpenMP. We have got this picture from Intel. I think it's better to show you the complexity by using this picture. If you have workload to offload to the GPU, this is the target device. Target device means GPU pretty much for OpenMP. And we have seen this target keyword here in this directive. Basically, that means GPU. So you use GPU to you offload to the GPU. You use this target device. Target offloading is here, and OpenMP target means that you are going to offer this workload to the GPU, and you need to deal with the teams, OpenMP teams. You need to distribute the workload between teams, and then you need to tell the runtime the distribute how to distribute the workload between the teams. And afterwards, if you have a for loop, you need to tell the runtime system how do you want to do the parallel for the for loop in your program. And then you need to tell the runtime system how to use this SIMD. Okay, so we do see the complexity of the OpenMP offloading. The complexity is pretty much with OpenMP. As a programmer, you need to tell the system, I want to offload the workload to the GPU. This is the target. And I'm going to, I need to have teams, okay? And I need to distribute the workload between teams, okay? And then you need to distribute your workload between the teams. And you are going to, I mean, for OpenMP offloading, pretty much we are going to work with the for loop. And you have to convert your for loop from the sequential one to a parallel one. So the for loop has to be dealt with. We know that for for loop to be executed in parallel by a number of threads, you have to separate the loops. If your loop is from 0 to, let's say, 1024, if you have two threads, you have to ask the first thread to work with the first 512, and the second one will be working with the another half. So if you have millions of threads, your parallel for loop has to be separated, has to be distributed onto these millions of threads. Each thread is going to be working on just a very tiny part of this for loop. And then you need to work on with SIMD, how the SIMD will be dealt with. So if you follow this one, you have your workload here. It has to be separated into 4 teams. And then you are going to distribute your workload if there's a for loop, the for loop need to be distributed onto different threads, and each thread has to deal with the SMD stuff. So conceptually, it's very easy to do. I mean, it seems very easy. You just need to write these directives in your code, and that could be done by the OpenMP runtime system for you. The parallelization could be done by the runtime, but in reality, it's not so easy. You need to really to understand the complexity of this kind of workload, offloading by OpenMP, and then you need to be careful with your choice of the directives, because there are a lot of parameters for these directives. You have to carefully work on these directives to have your final result, to have your workload really very well offloaded to the GPU. Okay, so we just have a very short introduction of this OpenMP directive offloading. Okay, to the last slide of this part. GPU computing has been here not so many years. I mean, maximum 1 decade. Maximum 1 decade. I mean, if you look at this MPI, MPI has been here, let's see, 3 decades or 4 decades. It has been evolved from the beginning. If you look at the history, at the beginning, there are roughly 20 standards to compete each other to be the standard as for message passing computing. And there are 20 standards. At the end, right now, from the marketplace, we have this MPI, the standard MPI, and then we have also MPI-CH. That's right now, in 80s, we have, I think that's around 20 MPI standards try to compete to each other to be the final standard. That includes the MPI, the MPI-CH, and there are some PVM, I think, and there are quite a lot of standards from different vendors, from different labs. And after, let's say, 3 or 4 decades, right now from the marketplace, we have the standard MPI, the standard by the MPI forum, which is the widely used standard. And on the marketplace, at the same time, we have a few other MPI, not standards, MPI products. That's a deviation from the MPI forum standard, the widely used one. That includes MPI-CH, okay? And that includes, I think that includes the Cree MPI, and maybe a few others. So we had 20 standards competed each other to be the final one. We have only one winner, and we have a few more others still available from the marketplace. There's a deviation. There are deviations from the standard, but that works, and that has been supported by Gray and by somebody else. So we know with the passing of the time, some standards will be dead. I mean, a lot of these products or standards has died out. It has only at the end we have only one, only the the biggest one, MPI. Everybody has been joined this MPI. Right now, this is the situation. Right now, let's have a look of this GPU computing landscape. How many offloading models, how many offloading standards here are trying to be the winner, let's say 2 or 3 decades later, or 1 decade later, or 10 years later. Okay, in the previous discussion, we have discussed the CUDA. We have discussed the heap for CUDA and for heap. What we have this kernel offloading. The kernel offloading for Nvidia that's supported here. For heap that's supported here. These two are the kernel offloading. Okay, we have discussed this one, and then we discussed this one, which is the reactive offloading. Okay, we discussed two methods of GPU offloading from the marketplace. Two methods. The first one, the kernel offloading, supported by two vendors, the two leading vendors, Nvidia and AMD. Okay. And the OpenMP directive offloading is the directive offloading is supported by the organization, the standard organization, OpenMP. I cannot remember the name of the organization for this OpenMP standard. It's the organization. The standard from this organization is OpenMP. So it's supposed that this directive offloading should be okay with the three vendors, because this is from this directive offloading is from OpenMP, the organization, and it should be supported by the three vendors. And we have this kernel offloading supported by the two vendors. I don't know the situation with Intel. For the moment, the situation with Intel is not so good, so I don't have too much information. Okay, we have discussed. That's what we have discussed. But let's have a look of what we have from the marketplace. We have plenty of other offloading methods. The SQL is another standard. The OpenACC is another standard. Okay, the Cocos another standard. There are Alpaca another standards, and we have some others. I think that has not been listed here. Somebody is saying OpenACC is dying because we have got this OpenMP coming into the scene. So OpenMP is dying. Somebody is saying this one. I don't know. I'm just repeating this. So right now the situation, let's see this way. The GPU computing is as a starting point. It's for since 1 or 2 decades, we have so many wonders, so many players get into this field. They try to promote their standards. Okay, CUDA, HEAP, SQL, OpenACC, OpenMP standard, Cocos, Alpaca, a lot of others. All these products, and let's see, all these standards, all these methods, they are trying to be the mainstream one. They are trying to be the final winner because the market is here. For this particular market, we cannot have 10 or 20 standards, just like the situation in the 80s for the MPI standard is at the very beginning. What I mean is that with the time pass by, at the end, we are going to have a few products, a few standards. At the end, we are going to have a few standards for a few methods to do the offloading. For the moment, it seems the kernel offloading, this method, the kernel offloading, this method, supported by CUDA and HP, is the leading one. And it seems this directive offloading supported by OpenMP and I suppose it's also supported by the vendors should be the promising one. We don't know yet, 1 or 2 decades later, which offloading methods we are going to use. Maybe the kernel offloading and directive offloading will be the winning one. Maybe that should be the winning one because that falls into the basic concept of OpenMPD. This comes from the shared memory stuff, and it seems this is promising. And it seems this kernel offloading is promising. That comes from the language functional call. Functional call. So it seems these 2 methods are promising. Maybe at the end, we are going to have these 2 winners. Maybe somebody else is going to win at the end. We don't know yet, but right now it seems these 2 are promising. So, okay, this is the end of this part. The last topic for this part is that we had a look at the marketplace. We had a look how many standards there out there in the marketplace trying to be the final winner. And this situation is quite similar to the MPI standard at its beginning in the 80s. There are so many standards trying to be the winner, and we don't know yet who is going to be the winner for the GPU offloading. And it seems kernel offloading and the directive offloading are the promising ones. Okay, by this slide, I'm going to end this part. So for this whole section, we discussed data parallelism. The conclusion is that for a technology to be successful in today's marketplace, it has to explore the data parallelism to deliver the performance to the industry. So vector processor had done that, superscalar processor had done that since AVX 512, and GPUs has done that since the very beginning by using the SIMT. Okay, and to offload the workload to the GPUs, we discussed kernel core, we discussed OpenMD offload. And we know there are many ways to offload workload to the GPUs because there are many standards out there in the marketplace trying to be the final winner. And we don't know yet who are going to be the winner. It seems right now kernel offloading and OpenP, the directive offloading, are the promising ones. So by this slide, I'm going to end this section. Thank you. I'm going to stop the recording.